Hi, and welcome to this part 3 of our tap block project video. And when we ended the part 2 the other day, we had just side milled the ends of the two blocks that I was roughing out. And if we recall, we had cut two blocks quite similar, but one being oversized on its primary and secondary dimensions by 10,000ths of an inch, and the other was pretty well size precise what we wanted. And I had side milled the two ends to give me some good references on my tertiary sides, okay? So that's important because that's going to help me a lot with the cutting off of my smaller blocks on the bandsaw and the cutoff bandsaw. And in this case, we're going to be cutting off 1/2 inch thick or wide blocks from this larger block. But that's a 1/2 inch finish dimension, so we're going to be cutting them a little over a 1/2 inch, leave some material on for finishing. First operation here is I put a little glue on the face here, and I'm going to lay out a line at a 1/2 inch from one of the ends. I'm not going to lay out all my parts, just one, and I'll use this to set up my cutoff bandsaw. So let's lay out that line. But before we do that, let's talk about this old height gauge and a trick to do with them, to use with them. This old style height gauge won't go under a 1/2 inch, or 1 inch in this case, as far as scribing a line from its reference base. So what do? Well, all we have to do is set our height gauge to 1 inch over what we want and raise our part. Here I'm using an accurate 1-2-3 block to raise the part by 1 inch. So I set my height gauge with its scribing tip at 1.5 inches from my reference surface, and I'm going to set up my part on a 1-2-3 block on the 1 inch side. 1.5 minus 1, I have the 1/2 inch I want, and now I can scribe my line. Okay, so I have my line at a 1/2 inch from the reference end of this part, and I'm going to use that line to go set up on the saw. Now I scribe my line at a 1/2 inch, which is the final dimension of this part. I'm not going to saw it off at a 1/2 inch. I'm going to leave some material on because I'm going to want to accurately finish this block to a 1/2 inch, and sawing isn't an accurate method for finishing the edge of a part like this. But we'll also see when we get to the saw in a few seconds that I'm going to have a hard time holding this part because this part is quite small. And as I cut my parts off of the main part, well, it's going to become even smaller. And I'm going to have a very difficult time holding this unless I make some type of special setup. And that's what we'll do. So let's head over to the saw and take a look at that. The problem here is that these vice jaws on this type of machine are made to swivel for angular cuts. And that means that if I'm holding a small part and I hold it only by the end, the vice jaws tend to pivot away and don't hold the part solidly because their edges aren't parallel to the reference surfaces they're trying to clamp. So what have I done here? Well, I've cheated a little bit. I've put a piece of mild steel, an accurate part, in the bottom that I'm going to use as support. And on the back, I've sandwiched in an accurate hardened parallel. And that's going to give me a nest that I can lean my part up into because the force of sawing here is going down and in that direction. And this will give me the support I want. Now, this vise can no longer clamp the part, however. So to get around that problem, I'm going to use a C-clamp. But before that, I want to show you why my stop here isn't touching the end, because I'm going to use this to set my position. And why am I doing that? When I cut a piece in a cutoff saw like this, or in any bandsaw really, at the very end of the cut, the saw has a tendency to want to grab onto the part because there's just a thin piece of metal left to cut, and it could hook into a tooth. When and if that happens, one of the two ends of the part has to be free to move. Now, if one end of the part is held in the vise or with a C-clamp, as we're going to do here, well, it can't move. And if the other end is leaning up against a hard stop, well, we have the ingredients there for jamming, bang, the part onto the bandsaw, because both parts aren't, one of the two parts aren't free to move. So if I use something accurate like this parallel bar, and I use that to set my position against the stop, well, once my part is positioned, I can take this away, and that gives me, in this case, a good 1/4 inch of movement, so that that part that's going to be cut off cannot jam onto the saw blade because it's stopped in its motion at the end of the cut when the part wants to go away. So that is very important for safety. On the bandsaw, you always want one end to be free to move. There, we can see that we're just past the line that I scribed, and that should cut a block to slightly over 1/2 inch and leave me some room for finishing. So let's take that cut. Okay, so I have my original part with one end cut off, and I have my first finished part, or semi-finished part, okay, that I have my 1/2 inch, a little oversized cut off that it's going to require some milling. Next step, well, I'm going to deburr the end of the original part that I've just cut. I'm going to then flip the part over and do the exact same thing on the other end, since I have a good reference surface on both ends. After that, I'm going to head back to the mill. I haven't undone my side milling setup, and I'm going to reinstall this part that by then will have no good ends on it, and re-side mill the ends to bring them back square so that I can produce 2 more parts. But before we get on with the machining, there's 2 things that I'd like to talk about, or at least to mention, so we can take a moment here. The first is, do you remember seeing just moments ago the part being cut off and how it was ejected at the end of the cut? And that's what I was talking about when I mentioned that the blade can grip onto the part, or grip the part, just at the very end of the cut. And we saw that happen. Now, had the stop, the positioning stop, been tight up against the part, well, there is a real possibility there that that part could have wedged between the stop and the blade, and ultimately the rest of the part that's held in my fixture here. And that could pinch the blade, and that can become a big problem. So, we have an example here of why we don't want those stops up against the part. And the second thing that we should mention is, a lot of you are going to write to say, that is a mighty small clamp you're using there to hold that part in the saw. Remember, holding parts in the machines is a question of force. But really there's 2 sides to the story. There's the force that the machine applies onto the part, and there's the force that we use to hold the part in place. Now, if I can counteract most of the forces that the machine will apply onto the part that I'm trying to hold, without actually clamping the part, just by using stops, well, I don't need that large of a force to fix the part into place. Let's take a look here at what we have. What we have here is three forces. We have a force that's going directly down. The blade applies a force directly towards the base here, and I've counteracted 100% of that force with this bottom support here. So the part is completely supported. None of that force needs to be held any more than that. Then there's an actual force here that the blade applies in this direction, and most of that force, I would say almost 98% of that force, is counteracted by this back parallel that I've sandwiched in. Now the only real force that I have to worry about here is the rotation around this point, okay, or the moment of inertia, but that's a whole other can of beans. We're not going to get into those big words, but this point here is a fulcrum that the part can rotate about if there's a force in that direction. And that very small force, because I placed the end of the parallel very close to the blade, you can see the curve here that it produces, and that means that I've left it no leverage whatsoever, or almost none. And that means that a very small clamp here is all that is required to keep this part well in place for this machining operation. Okay, so we took a moment to talk about a moment of inertia. Well, that joke wasn't that funny, but I felt like doing it anyways. Off camera, in the meantime, I went and cut the second end off of our part, and it's complete. It was the same as the operation as the first side, so there's nothing new to see there. And what do we end up with? With obviously two slightly oversized in the tertiary side, two slightly oversized blocks that will be finished later, and this leftover that is supposed to become three more small blocks. But I now have a block that has no good tertiary references. Well, I thought ahead and I left my setup on the mill, so we're just going to head back to the mill and re-side mill the ends to give us those good square references. And those references are going to make my life a lot easier later on when I come to do the finished milling of those small blocks. But I do have a problem here in that this block that I'm going to side mill is starting to get a little short. Actually, it's getting so short that the back end of the part, when it's in the vise, won't make it all the way to the axis or the center axis of the lead screw that I use to tighten the vise down. And what that means is that when I tighten the vise, I'm going to actually be cocking the movable jaw, and that means I'm not going to be getting a good contact on my part. So what am I going to do? Well, in this case, it's easy. I've just cut a block, or two actually, but I only need one, an accurate block off the end of this part. I'm just going to use that accurate block to support the back end of the vise and maintain the alignment or the parallelism between the movable jaw and the fixed jaw and ensure a good holding force on my part. So let's take a look at that. So that's one good reference end. What I'm going to do? Well, I'm going to get the part out of there, deburr the end that I just milled, flip the part over, and give myself a good reference end on the other end of the part, and I'll have two good reference ends. Then I head back to the saw to cut the first part out of that smaller block. Okay, so now I have 3 blocks roughed out, and I have this little stubby guy here that's going to become the 2 last blocks. But the last one that I'm going to cut is going to end up being a block with 2 surfaces that aren't good. So what I'm going to do to avoid that problem, because all I have is 1 cut left here, I'm going to cut this in 2 to get my 2 last blocks. Well, I'm going to head back to the mill right away. Instead of just flipping the block over and using that last reference, I'm going to head over to the mill the surface that I just cut on the saw so that I end up with this short piece with 2 good ends. And believe me, it's easier to mill it now before I end up with just a little 1/2 inch part to hold in the mill. So I'll hold this inch and something long part, mill the end, come back, cut it in 2, and I'll end up with my 2 last blocks. And that'll be 5 blocks that will become 5 tap blocks. And what do we end up with? Well, we end up with 10 usable parts. Now, the end part of each original longer part is a little bigger than the 4 others, but still quite usable. We'll just have to mill the second tertiary a little more. But what's important here is that I have 5 parts with 1 thou over for finishing by hand, and I have 5 parts with 10 thou over for finishing on the grinder. And even more important at this point is that each of these 10 parts has 1 good, nice and square tertiary end, and that makes my life really a lot easier. It makes my life a lot simpler because each of these 10 blocks has a good and reliable tertiary surface, and that means that when I head back to the mill in a few minutes to mill the second tertiary surfaces, I won't have to use an indicator or a square and try to realign things and get things nice and square. I don't need to do that. I already have a good reference surface. So if I sit that good tertiary surface right down onto my parallels, well, I'll be looking pretty and I'll avoid a lot of work. And that just comes to show us that a little planning at the start can save you hours and hours of work at the end of a project. So let's head back to the mill. We're going to reinstall our carbide insert face milling cutter and set up for cutting those tertiary surfaces. So I'm set up in the mill here, and if you recall, I had 2 sets of 5 blocks. I'm going to start with the higher of the sets, or the oversized set of blocks, the one that's 10/1000ths of an inch oversized in all directions. And of those 5 oversized blocks, I had one that was quite a bit longer than the others, and that was the end block, the last one that I produced on the saw. So I'm going to start by cutting it. I have it mounted in the center on a parallel, and I'm going to progressively come down to my 10/1000ths of an inch over a 1/2 inch dimension. And once I'm set, I think I'm going to be able to get away with cutting all the 4 other blocks of that series in one pass. And what I'll do then is mount them 2 by 2 and do 2 passes to finish those 4 other blocks. So let's start cutting away. Just what I'm going to do here, well, I have no really good reference surface on the opposing the tertiary surface, the one I want to cut here. I can't measure it precisely. So I'm going to take a skim, back off, give myself some room, not take the part out, but I'm going to measure it in place and define how much more I have to take off and then work my way down from there. So let's take that first cut. Point 657. If I take a look here, 0.657 minus 0.510 equals 147 thousandths of an inch to come off. Now obviously I'm going to take several passes. This is a small part and a delicate machine. But 147. So I'm going to shoot for a 140 and then remeasure before a final cut. So I've taken my final pass and I can see that I'm at 512 thousandths of an inch. That is fine for what I need here. I was shooting for 510, but remember it's 510 because it needs to be surface ground. So we'll be taking 6 thou per side instead of 5, and that's really no big problem. And if I measure both ends, well, I can see that I'm nice and parallel. So this block is complete. It's the first oversized block. And since the 4 other blocks are a lot closer to the dimension, the 510 dimension I wanted, I might just get away with cutting them without readjusting my height, just by passing them all at the same height. I'll set 2 next blocks up because the 4 next will be done in tandem, 2 blocks and 2 blocks. And we'll take a cut and we'll see what it's like and we'll measure them. And if they're good, well, we'll do the final 2 blocks. There, I've set up my 2 next oversized blocks, and as you can see, neither of them line up with the lead screw or the screw on the vise. That's because I don't want one held any better than the other. Now they're the same width, but I put them side to side of the center with a good distance between the two to make sure that the movable jaw that does have some play in it averages things out and holds each part evenly. So let's try that cut. So I'm around 511. The other one was 512. Really no problem. There can be slight differences here. I mean, 1 thou or even 3/4 of a thou isn't very much. And that cut was a lot bigger than the last cut on the first part. So it's to be expected, but we are well within what we wanted to get. So we still have 2 pieces to cut at this dimension And then we have our 5 pieces to finish at the almost size per size dimension. And well, we'll be doing those a lot easier because we already know exactly where we are. If I take about 9 or 10 thou more of a cut than what I'm actually doing, I'm going to be right where I want for those 5 other parts. So they're going to be easy to do. So I'll see you back at the workbench when I'm done all those blocks. And what we end up with, well, is 10 blocks. 5 oversize, 5 size per size, and all from a piece of steel that was the same size as the piece of steel used to produce this 1, 2, 3 block. So a little bit of planning can really help on saving material. Well, these parts may be small. Actually, they're tiny. They're about the size of 2 cubes of sugar. But they do end up having a lot of holes drilled into them. Actually, we're going to be drilling 7 holes in each of these blocks. So we'd better start looking at our plan, our drawing, so that we can plan an attack. How are we going to go about drilling these holes to not get ourselves into trouble?
Here we have a 3-view third angle projection drawing. We have a front view, a right side view, and we have a bottom view. We can also see that the outside dimensions of the block are directly affixed to the views, but that the diameter of the holes and the hole positioning is not part of the projection. They're found in the table to the right of the drawing that is actually a Cartesian coordinate table. The first column of this table is the hole identification letter. Next comes the x-axis coordinates, then the y, and finally the z. The last column has to do with the hole's diameters. It's good to notice here that we have holes in our XY plane, and we also have holes in our XZ plane, but there are no holes in the YZ plane. We can also see that all the holes have different diameters, and that means that there's going to be a lot of tool changes to look forward to. And that's why it would make sense, since we're producing 10 of these blocks, to plan a sequence of drilling that will reduce to a minimum the number of tool changes required. But before we get into the part itself, it is crucial to take a good look at the header and the notes on the drawing. First thing to say about the notes is that they aren't in the proper order, and they rarely are. In reality, we would harden and temper to 4045 Rockwell first off, once the part was all rough machined. Then we would grind all the exterior surfaces, and finally we would remove all the sharp edges. Now, if we take a look at our header, we'll see that it's the description, the material, and the tolerances that interest us the most. Let's start with the tolerances. We can see that unless otherwise specified, and on this drawing there are no specified tolerances, well, unless otherwise specified, 2 points and 2 numbers after the decimal point, it has a tolerance of plus or minus 10 thousandths of an inch, and 3 numbers after the decimal point has a tolerance of 5 thousandths of an inch. And that means for us on this project that the outside dimensions of the blocks have a tolerance of plus or minus 5 thousandths of an inch, but that the positioning of the holes on those blocks have a tolerance of plus or minus 10. So I guess we could say that the grinding operation on this block, since the external dimensions aren't that accurate, isn't really required for the dimensions. It's more required for the look, because after the heat treatment, the exterior surfaces are pretty rough. This also tells us that for the positioning of the hole, laying out, punching, and drilling would be more than accurate enough, because really a plus or minus 10 thousandths of an inch tolerance on hole positioning doesn't require using a milling machine and coordinates. If I look up to the top right corner of the header, I'll see that the suggested material is 4140. And if I was producing this part for a client, well, I'd use 4140. But for the home machinist, really, any medium carbon steel will do just fine. As for the description, well, we can see that we're looking for, as far as a minimum size of material goes, a 5/8 by a 1/2 inch by 1 piece of medium carbon steel. Now, if you can find a cold rolled piece of 5/8 by a 1/2 inch and cut it at a 1 inch length, well, you're going to have very little milling to do, because the 5/8 and the 1/2 inch dimensions will already be within the tolerance required. You'll really just have to get that 1 inch dimension down to its proper size. Now, I went through a lot of trouble to produce my 10 parts from a piece of 2 by 3 inch bar stock, but that's just because I had that bar kicking around and I wanted to use it. It's not because it was the best size to start off with. So now let's get back to our part and take a look at those 7 holes. As I've already mentioned in the 1, 2, 3 block project, when we have intersecting holes that intersect on their center lines, well, we usually try and drill the longest holes first. And if possible, we try and drill the largest holes first. And in this case, we can do that for all the holes except for the D hole. D hole here is a problem. It's a problem because it intersects the F hole, but not on its center line. It really just intersects the edge of the F hole. And since D is very small, well, that drill will be affected by the lack of material if it goes through the F hole just a little bit as we're drilling that small D hole. The answer here would be to drill the D hole first, and then drill the F hole. Since F is quite massive and just barely touches the D hole, it won't be affected, or at least very, very little affected, by that very slight overlap. Now, if we did it the other way around, if we drilled the F hole before the D hole, well, the D hole would be really quite affected because the drill is so small and flexible that it would deflect and probably would want to turn into, or at least towards, the larger F hole. So that means that the order of drilling here is going to be D first, followed by F and G. And then we can produce in any order B, A, C, and E. The order of those last 4 holes really isn't important. Now, this part could have very well been designed in a way that the D hole would not have intersected the F hole at all. Actually, it would have been quite simple to design it that way. But this is a learning process, and the problems caused by intersecting holes that don't intersect on their center lines, well, are real, and it's important to be aware of this type of situation.
Well, that's enough for this time. Next time we'll be looking at drilling holes, and we'll be drilling holes in these little cuties. So until then, have fun, be safe, and happy machining.
There you go.